10th Standard Geometry, Chapter 3, Circles, Module 2. In this video, we will be learning about touching circles. Let us recall what we have studied in our previous video. First, a tangent at any point of a circle is perpendicular to the radius at the point of contact. This is the tangent theorem. Second, a line perpendicular to a radius at its point on the circle is a tangent to the circle. This was a converse of tangent theorem. Third, tangent segments drawn from an external point to a circle are congruent. This was a tangent segment theorem. Now, let us continue further. Touching circles. Let us understand the definition of touching circles. Touching circles can be defined as follows. If two circles in the same plane intersect with a line in the plane in only one point, they are said to be touching circles and the line is their common tangent. There are two types of touching circles. First, externally touching circles. In the figure, circle with center R and circle with center S touch each other externally at point P. A line passing through point T will be a tangent and a common tangent to both the circles. Second, internally touching circles. Circle with center N and M touch each other internally at point T. A line passing through point T will be a common tangent to both the circles. Next is the theorem of touching circles. Let us understand the statement of this theorem. The theorem states that if two circles touch each other, their point of contact lies on the line joining their centers. So, given C is a point of contact of the two circles with center A and B. Now the two circles can be touching externally at point C or they can be touching internally at point C. So C is the point of contact of the two circles with center A and B. We have to prove that C lies on the line AB. So we have to prove that C lies on the line AB. Note that AB is a line joining the centers. Let us start with the proof. Let line L be the common tangent passing through C of the two touching circles. So line L is a common tangent that is passing through point C in both the cases if it touches externally or if it touches internally. Line L will be perpendicular to AC. Since line L is a tangent and AC is a radius, by tangent theorem we can say that L will be perpendicular to AC. Similarly, we can say that L will be perpendicular to BC. Therefore, segment AC is perpendicular to line L and segment BC is perpendicular to line L. Now we note one thing, that through C, only one line perpendicular to line L can be drawn. Therefore, we can say points C, A and B are collinear. The definition of collinearity is points lying on the same line. Therefore, C, A, B lie on the same line, and hence from here we can say that point C lies on segment AB and AB is a line joining their centers. Hence, point C lies on the line joining their centers. Next, a few important points to remember. First, the point of contact of the touching circles lies on the line joining their center. This is same as the touching circle theorem that says the point of contact of the circles, if they touch externally or internally, then the point of contact lies on the line joining their centers. The second point, if the circles touch each other externally, distance between their center is equal to the sum of their radius. In the diagram, you can see circle with center A and circle with center B touch each other externally at point C. R1 is the radius of the circle with center A. R2 is the radius of the circle with center B. AB is the distance between their centers. So if we want to find distance AB, we add R1 and R2. So R1 plus R2 is nothing but the distance between their centers. Third point, the distance between their centers of the circles touching internally is equal to the difference of their radii. In the given diagram, circle with center A and B touch each other internally at point C. R1 is the radius of the circle with center A. R2 is the radius of the circle with center B. AB is the distance between the centers. So to find the distance AB, we subtract R1 from R2. So R1 minus R2 will be the distance between the center. Practice set 3.2, the first sum. Two circles having radii 3.5 centimeters and 4.8 centimeters touch each other internally. Find the distance between their centers. So here in this case, the two circles, the radius of the bigger circle is 4.8, the radius of the smaller circle is 3.5, and the two circles touch internally. We have to find the distance between their centers. Solution, it is given that two circles having radii 3.5 centimeters and 4.8 centimeters touch each other internally. We know the distance between the center of the circle touching internally is equal to the difference of their radii. So, therefore, distance between the center of the two circles is equal to 4.8 centimeters minus 3.5 centimeters, which is 1.3 centimeters. Thus, the distance between their center is 1.3 centimeters. Here we have used the third property that says if the circle touch each other internally, then the distance between the radii is R1 minus R2. Practice set 3.2, the fourth sum. In the given figure, the circle with center P and Q touch each other at R. A line passing through R meets the circle at A and B respectively. Prove that first, segment AP is parallel to segment BQ. Second, triangle APR is similar to triangle RQB. And third, we have to find angle RQB if angle PAR is equal to 35 degrees. Let us understand the question. So it is given that circle with center P and circle with center Q touch each other externally at point R. A line passes through the point R and it meets the circle at A and at B. So we have to prove the following three questions. Let us start with the proof. The first, we have to prove segment AP is parallel to segment BQ. In triangle APR, AP is equal to RP as they are the radius of the same circle. Therefore, angle ARP is equal to angle RAP. The reason being, in a triangle, equal sides have equal angles opposite to them. That means angle opposite to equal sides are equal. Therefore, angle ARP is equal to angle RAP. Now in triangle BQR, QR is equal to QB as they are the radius of the same circle. Therefore, angle RBQ is equal to angle BRQ. The reason being, in a triangle, equal sides have equal angles opposite to them. Or we can say that angles opposite to equal sides are equal. Also, angle ARP is equal to angle BRQ as they are vertically opposite angles, and we know that vertically opposite angles are equal. So from 1, 2 and 3 we have angle RAP is equal to angle RBQ. Therefore, we can say that segment AP is parallel to segment BQ. The reason being is if a transversal intersect two lines such that a pair of alternate angle is equal, then the two lines are parallel. So AB is a transversal and it intersects the two lines at a pair of alternate interior angles, hence they are equal. Therefore, AB should be parallel to QB. The second part, to show triangle APR is similar to triangle RQB. In triangle APR and triangle RQB, angle RAP is equal to angle RBQ. This we have proved in the previous part. Also, angle ARP is equal to angle BRQ as they are vertically opposite angles. Therefore, triangle APR is similar to triangle RQB by angle-angle similarity criteria. The third part, we have to find angle RQB if angle PAR is 35 degree. Angle PAR is equal to angle ARP and both of them are 35 degree. Also, angle ARP is equal to angle PRQ and they are 35 degree. Also, they are vertically opposite angle. Hence, angle BRQ is equal to angle QBR, which is also 35 degree. Now, in triangle RQB, by angle sum property, if we add all the angles in a triangle, it will be 180 degree. We know that two angles in this triangle are 35 degree, BRQ is 35 and RBQ is also 35. So 35 plus 35 will be 70. Take the 70 on the other side, we get RQB is equal to 180 minus 70, which is 110 degree. Thus, the measure of angle RQB is 110 degree. Next, practice set 3.2, the fifth sum. In the given figure, the circles with center A and B touch each other at E. Line L is a common tangent which touches the circle at C and D respectively. Find the length of segment CD if the radii of the circle are 4 cm and 6 cm. Let us understand the question. Circle with center A and circle with center B touch each other externally at point E. Line L is a common tangent to both the circles and it intersects the circle at point C and point D. We have to find the length of segment CD and radius of the smaller circle is given 4 cm. The radius of the bigger circle is given 6 cm. Let us start with the solution. If two circles touch each other externally, then the distance between their center is equal to the sum of their radii. Therefore, AB is a distance between the centers of the two circles. AE is a radius of the smaller circle and EB is a radius of the bigger circle. So AB is equal to AE plus EB. AE, that is the radius of the smaller circle, is given 4 centimeters, and EB, that is the radius of the bigger circle, is given 6 centimeters. Therefore, 4 plus 6 is equal to 10 centimeters. Therefore, AB is equal to 10 centimeters. Next, it is given that L is a common tangent which touches the circle at C and D. Therefore, angle ACD is equal to angle BDC is 90 degree. If you look at the figure, AC is a radius of the circle with center A, line L is a tangent, and by tangent theorem, we know that the tangent is perpendicular to the radius. Hence, AC is perpendicular to line L. Similarly, we can say that BD is perpendicular to line L. Since they are perpendicular, they will be 90 degree. Therefore, angle ACD and angle BDC will be 90 degree. Hence, we can say angle ACD equal to angle BDC is equal to 90 degree. Next, we do a construction. We draw AF perpendicular to BD. If you see in the diagram, we have drawn AF perpendicular to BD. Here, in rectangle ACDF, CD will be equal to AF and DF will be equal to AC, as they are the opposite sides of rectangles, and opposite sides of rectangles are equal. So since AC is 4 centimeters, DF will also be 4 centimeters. Therefore, DF equal to AC is equal to 4 centimeters. We know that BF, if you see in the diagram, BF plus FD will be equal to BD. BF plus FD equal to BD. We know that FD is 4 centimeters from the previous step. We substitute 4 in place of FD, and we know that BD, that is the radius of the bigger circle, is 6 centimeters. We take the 4 on the other side, therefore we get 6 centimeters minus 4, which is 2. Therefore, BF is 2 centimeters. Now, in triangle ABF, by construction, AF is perpendicular to BD, so this triangle forms a right angle triangle. Hence, we use Pythagoras theorem, that is AB square is equal to AF square plus BF square. By substituting and simplifying, the value AB is 10 and BF is 2. We substitute the values and simplify, we get AF to be under root of 96, which is equal to 4 root 6. So length AF is 4 root 6 centimeters. But CD is equal to AF. If we look in the previous step, opposite sides of rectangles are equal. We have showed that CD is equal to AF. Hence, CD equal to AF have the same length. Therefore, CD is equal to 4 root 6 centimeters. Let us revise whatever we have studied. First, the point of contact of the touching circles lies on the line joining their centers. Second, if the circles touch each other externally, then the distance between their centers is equal to the sum of their radii. Third, the distance between the center of the circle touching internally is equal to the difference of their radii. Thank you.